Recording. Okay, so today we're going to talk about chapter 9, isomorphism. Yeah, so this is a very uh, famous topic, right? So what does it mean to call two things isomorphic? And I couldn't help but notice that the way that this author chose to talk about it, it really, especially this paragraph, the dictionary tells us that two things are isomorphic, they have the same structure. Is it is an expression of the simple fact that objects may be different in substance but identical in form. And this really reminded me of the ship of Theseus thing. Wikipedia. Yeah, so I recommend people reading about it because this is essentially like talking about this idea that there is something. What does what does differentiate something out of everything else? Uh, yeah. Anyway, so in geometry, there are several kinds of isomorphism, the simplest being congruence and similarity. Two geographic figures are congruent if there exists a plane notion which makes one figure coincide with the other. They are similar if there exists a transformation of the plane, magnifying or shrinking lengths in a fixed ratio, which again makes one figure coincide with the other. So this is rotation, and this is changing the size. And then you have two palindromes that we can make Madam and Rotor be the same palindrome if you do a particular transformation which is describing here, right? So, well, actually, this paragraph is more about these two networks here. So, what is the transformation that makes network A the same as network B? And this is the function, right? One that maps 1 to 6, 2 to 5, 3 to 8, and 4 to 7. And this is called an isomorphism from network A to B for it transforms A into B. Which brings the first contentious point. When we learned about isomorphism back in the category theory book, this is not enough. So I wonder who is wrong.
Nobody, because this is just talking about one half of the isomorphism.
That's not written there. There's no word half in here. And then not even in the definition, which we're going to get through in a minute. And I noticed that. And I noticed that. Because I was the one that kept using this word wrongly. And Marinho was the one saying, Lemos, that's only half of it. So I have a very concrete notion in my head that you must say both ways. And this isn't. So again, and by the way, which is it makes the problem even more concerning to me is that there is an exercise asking for us to prove the other half, but it is not in the definition.
Well, it is
So
implied by the definition, but never spelled out.
I disagree. We're gonna get through the definition, but I disagree that the definition implies that. I very strongly disagree. But let's go through everything else before the definition. Uh, okay, so essentially, we're gonna get through that, and then you can the palindrome problem can be solved by using this function, and it is saying that this correspondence is an isomorphism. Our next and final example is from algebra. So again, using the groups idea. So we have two groups, G1 and G2, and you have the table of G1 and the table of G2, with the operation on G1 being plus and the operation on G2 being multiplication. And it is saying they are different but isomorphic. And the reason is because you can go from G1 to G2, as it's written in here. And this is the function that does that. So if you swap 0 in G1 by E, 1 by A, and B in 2 by B, you're going to get the same table as the table of G2. And it transforms G1 to G2. It is called an isomorphism from G1 to G2. Finally, there exists an isomorphism from G1 to G2. G1 and G2 are isomorphic to each other. In general, by an isomorphism between two groups, we mean a one-to-one correspondence between them, which transforms one of the groups into the other. If there exists an isomorphism from one group to the other, we say that they are isomorphic. And this is the beginning of my problem. But we're gonna get more specific. If G2 and G1 and G2 are any groups, an isomorphism from G1 to G2 is a one correspondence F from G1 to G2 with the following property. For every pair of elements A and B in G1, if applying F to A goes to A prime, and applying F to B gets you B prime, then FAB equals to A prime B prime. Can somebody help me understand why do we need this? Like, this is 100% necessary because the step-by-step process we're going to get through has that specifically written in there. So why is that required?
It says that you have a mapping between the elements, but that the operation is also the same.
Well, the operation is not necessarily the same, but it has
Oh,
the same
it does the
structure.
same thing, yes.
Okay, so you're essentially lifting the operation. You're mapping the operation itself, but we are representing that extensionally using the elements. So that's what you mean, Tev?
Yes, that says that the operation on the mapped elements has the same effect as the operation on the original group.
Okay, I see. It is easy to see that if has this that if it has this property transforms the table G1 into the table of G2. And this is a very interesting point. I never actually thought of that in that manner. But this is essentially saying that you can view isomorphism as an alpha conversion thing.
Well, alpha conversion is not really an isomorphism because it's not unique, but yeah, it is in fact a way to like get a different lambda expression that has the same structure and the same semantics by just replacing some labels, right?
Yeah. I wonder how many mathematicians are pissed about this take because we are kind of saying it's a syntactical thing in a way. I know it's not like only syntactical, but explaining in this way makes it seem like it is. Uh, because it's like concretely using the renaming verb. By the way, property 1 may be rewritten more concisely as this, and we may sum up our definition of isomorphism in the following way. Um, let G1 and G2 be groups. A bijective function f that goes from G1 to G2 with the property that for any two elements A and B in G1, this holds, is called f is then called an isomorphism from G1 to G2. Which, if we ended in there, I still think the book would be. Would still be weird that so far we haven't mentioned that it's about you having the two halves. But it would not be that bad. But I think this is I have a problem with this thing. If there exists an isomorphism from G1 to G2, we say that G1 is isomorphic to the G2. And in my understanding, if you remove this qualifier and you just say this, then I assume that one of the authors must be wrong.
By the other half, you mean that mentioning the other way around from
Yeah.
Q2 to Q1.
Yeah, if you flip
That
the
is
arrows of
that is
the
implied by the fact that the function is bijective.
You are saying that because it is bijective, it is invertible, which then means that if you just do prove one way, the other way is given because f is bijective?
Yes, because it has an inverse for every
essentially.
element of the set of G2.
Does that justify not being written? I guess I'm gonna have to concede that pedantically Tevu is 100% correct because f must be bijective, which means that it's guaranteed to be invertible. But I still think that saying that isomorphism is about just this and letting the reader essentially infer that the other half is also implied because f is bijective, I don't know. I think that you were assuming too much at that point. This is a book about teaching anyway.
Well, there is an exercise where he says the
Well,
opposite and asks you
but
to prove it.
that's still bad if it's an exercise. That should be written in here as it was in the category theory book. And I would say that the other book had the obligation of saying that because we didn't talk of the mappings specifying the properties of being bijective or not, right? So in there, it was actually mandatory, not only a nice to have, but a must have. In here, it would be just a good to have because at least you can say that actually, pedantically, f is bijective, then I don't have to write that. But as a reader and as a student, I would be very disappointed by that. If there exists an isomorphism f from G1 to G2, in other words, if G1 is isomorphic to G2, we symbolize this fact by writing this operator. How does one recognize if two groups are isomorphic? That's very interesting. So, um, first of all, if there exists, if G1 and G2 are isomorphic, if there exists an isomorphism, and then there is a problem of finding one, right? So some of them are trivial, some of them are not. And then if you have a guess, right, which the author is making an educated guess, which is essentially is like, I don't know what makes a guess educated or not, but sure. And then we have to check. So first of all, we have to check if f is bijective, right? So that cuts the options a little bit, and then we have to check if the operator is also being mapped, right? The operation itself, which is checked by this equality. And then we have any examples of the numbers with the operation of addition, and then the positive with the multiplication, and then the educated guess is the exponential, and then you check that it is bijective, and you check that the operation itself is also lifted by checking that this is true. And this, yeah, and you must be aware that the operation on the left side, it must be different than the operation of the right side, precisely because the operations in the two different worlds may be different. And how does one recognize when two groups are not isomorphic, right? And it says that it's easier to find like candidates that don't fulfill those properties, those not properties, the checklist. And then there is this tip here: if a group G1 has a property which the group G2 does not have, they are not isomorphic. Which this is just like badly written because immediately after he makes a counterexample of what he just said. So like, why would you do that yourself? But then he qualifies it, right? So that there is this sentence here that you must be talking about properties that are not dependently married on the names of the assigned individuals. But this sentence should be actually be up here. Because why would you do that yourself? And then you have that examples of properties that usually are important to notice. So like G1 is commutative, or and G2 is not. G1 has an element which is its own inverse, G2 does not. G1 is generated by two elements, whereas G2 is ungenerated by any choice of two of its elements. Perhaps every element in G1 is the square of the element is a square of another element where G2 does not have this property. This is not exhaustive. You should care to watch for properties which do not depend merely on the names. So for example, if 0 is part of G1 and 0 is not part of G2, that is something different, but you cannot just immediately say based on that they are not isomorphic, because in this case they are. And then finally, if G1 and G2 cannot be put in one-to-one correspondence, clearly they cannot be isomorphic. And then it comes a very cool thing, that apparently in the beginning of times, the groups that the mathematicians cared were only the groups of permutations, which is kind of silly if you think about it, but well, maybe that's anachronic, right? There's something comforting about working with tangible things such as a group of permutations of a set. But then later, as we saw the chapter 1, the axiomatic method reshaping algebra, Now it can be anything, and it's like more general because it allows many new things to be groups, which would not be groups of permutations, obviously. And then actually a guy said, you know what? I'm actually going to bring those two things together, and I'm going to prove that every group is isomorphic to a group of permutations. Roughly, this means that the groups of permutations are actually all the groups there are. Like you can actually grab all the groups and put them in a bucket with a particularly common property, which is that they are all groups of permutations. So that's the theorem. How do you say his name? Cayley's maybe? Cayley?
I'm pretty sure it's Kaylee.
Okay. Let G be a group we wish to show that G is isomorphic to a group of permutations. The first question to ask is what group of permutations and permutations of what set? After all, every permutation must be a permutation of some fixed set. Well, the one set we have at hand is G, is the set G. So we had better fix our attention on permutations of G. The way we match up elements of G with permutations of G is quite interesting. So with each element A in G, we associate a function pi from G to G, which is an automorphism or whatever. So the pi function just essentially multiply the on the left by A, and then you may ask yourself why the left and not the right. There's an exercise about that. We will now show that pi A is a permutation of G. Pi A is injective. We have to prove that it is bijective, right? So we need to check if it's injective. First, if this is true, then this must be true. So by cancellation law, x1 is equal to x2. So we are essentially proving that injective is that we are using all the elements of the domain, right?
That's surjective. Injective is every element of the domain
Goes to a different thing.
goes to a different thing
What I said is
on
not
the.
surjectivity because I said domain, not image.
Oh, domain. Every function has to use everything in the domain, right?
Yeah, that's the definition of a function. Yeah. And then surjectivity is if you're using everything in the image. So
Yeah.
imagine a y in G. If you write y, well, you can rewrite y to just be this because this is just identity, right? So, and then you can say that because A is on the left, this is pi I of this thing in parentheses, thus each y in G is equal to pi I of x, which means that you are x is equal to the inverse of A times, y, which means that it's surjective, and then it means that it is bijective, which means that pi I is a permutation of G. Let us remember that we have a permutation pi I for each element A in G. For example, if you have a B and a C, they all do that. So you can write that as that. Observe now that G star is a set consisting of permutations of G, but not necessarily all the permutations of G. In chapter 7, we use the symbol Sg to designate the group of all the permutations of G. We must now show that G star is a subgroup of Sg. For that, we'll prove that G is a group of permutations. To prove that G star... Wait a moment, why do we need to say that, like... okay. It's because if we only have a set of permutations, not a group. To have a group, we have to have the neutral element, inverse, and blah blah blah, associativity. And we want to say that this is a group. We're going to exploit the fact that there is a relationship between the G star and Sg. Okay. To prove that G star is a subgroup of Sg, we must show that it's closed with respect to composition. The definition of subgroup essentially, which means you are composing on yourself. You're compose, and the outcome of that is within yourself, and you're also closed with respect to the inverse. We must show that pi I and pi b are any elements of G star. The composite is also in G star, and the inverse of any pi A is also in G star. So we can write the composition as this to show that this and they are the same. We must show that they have the same effect on every element. This is very easy to conclude. And this proves that the composite of any two members ZA, and this is wrong, right? Should be pi A.
Yeah, that's a typo.
And pi B of G star is another that which is also lives in G star, and then it is closed in respect to composition. It is easy. This is also a typo in the printed version. It is easy to see that pi E is the identity function. Indeed, this that. In other words, P is the identity element of SG. Finally, by equation 3, uh, yeah, this is also,
Yeah, that those minus ones should be subscripts.
they should definitely be subscripts. So by theorem 2 of chapter 4, the inverse of pi A is pi A minus 1. This proves that the inverse of any member pi A of G star is another member in G star. Thus, it is closed to respect of inverses. Since G is closed with respect of both of these two things, G star is a subgroup of SG. And then it's kind of a big deal. We're now in the final lap of our proof. We have a group of permutations G star, then it remains only to show that G is isomorphic to G star. To do this, we must find, and why we need to do that? Because G is the arbitrary group, and G star is the group of the permutations of G. Well, actually, that's what we want to prove, right? So this, well, that is true, but we want to prove that they are isomorphic. To do this, we must find an isomorphism, f, that does that, and let f be the pi function. In other words, f matches each element a in G with the permutation pi a in G. We can quickly show that by doing the checklist. So f needs to be bijective, which means proving it is injective and surjective. So indeed, if fa is equal to fb, then pi I is equal to pi b. Thus, we can just put any element in there. That's going to be equal to that. And by cancellation law, we can just do that. So it is injective. Because if they have the same image, they must be the same. So it is injective. F is surjective, so every element of G star is some pi I, and pi I is equal to f of A. Yeah, I said pi I is pi A, sorry. And lastly, the property that we are also mapping the operation itself, right? So FAB is equal to pi AB, which is equal to their composition, which is equal to the composition of F's. Thus, F is an isomorphism, and we just proved that. So what we can say then is that you can always translate any group to a group of permutations in respect to the elements of that group. And we can then just apply all that we learned in the previous chapter about permutations. Cool. Okay, so exercises. So exercise A is about proving some stuff. Yeah, so this is where we need to prove the other way around, and you can do that by what Tevo said, right? So because f is bijective, that means that it is guaranteed that there exists an inverse, and that is going to be, you're going to have to prove that that is also isomorphic from G2 to G1.
It's kind of funny that points 1 and 3 together, they actually mean that isomorphisms between groups form a category, essentially.
I forgot. Why would that be true?
Because point 1 says every group is isomorphic to itself, so there is an identity morphism for every
Yes.
object.
Yes.
And then 3 is just the composition law.
I was about to say this is transitivity, but you are right. This is also composition. Yeah, and that is composition. Yeah, and these exercises are in regards to these three facts. So let G be any group, and then we have the identity, which is to say that E is going to be identity is going to be an isomorphism to itself, because it will always be bijective by what identity is. and the compositions of identities also like this thing is also gonna work. So it is definitely an isomorphism. Let G1 and G2 be groups and F be an isomorphism. So we have to show that there is an inverse of F, and we know that's true because it is bijective. We just have to show that the inverse is also isomorphic. Review the discussion of inverse functions for arbitrary elements, blah blah blah. Yeah. Let G1, G2, and G3 be groups, and we have to check that the composition of our isomorphisms is also isomorphic. Well, form an isomorphism, I should say. Okay, anything to comment about exercise A? We should be very picky today because again we have all the way to J.
Uh, Other than the connection to categories, not really.
Elements which correspond under isomorphism. Recall that an isomorphism F from G1 to G2 is a one-to-one correspondence between G1 and G2 satisfying that. F matches every element of G with a corresponding element of G2. Man, how... Now I want to test that out. How much of a rage bait would be if I just say that an isomorphism is alpha conversion? It is important to know that those things. So F matches the neutral element of G1 with the neutral element of G2. If F matches an element G1, X in G1 and with Y in G2, then necessarily F matches their inverses. That is, well, yeah, what I just said. And F matches the generator of G1 with the generator of G2. So these are more like consequences of the way that we described it. But I don't really know how I would how I would prove those things myself, right? So because we have to prove that if you have an E1 denoting the neutral element of G2 and an E2 denoting the neutral element of G2, how are we going to prove that applying F to E1 is going to go to E2? I have a probably intuition that this is going to be proved by contradiction, but how would you guys do it?
Most of those are consequences of the additional constraint that you have to respect the algebraic structure.
Do you mean the third check?
Yes, the one that the f of a composition of A and B has to be equal to the composition of f of A with f of B, right?
But how would you exactly would use that to prove that E1 would definitely be mapped to E2 under
Well,
F?
if you suppose that one of the elements, like A or B, is actually E1 in this case, right? Then the fact that it needs to respect the group structure would force it to be E2 because otherwise, if you cancel out E1 on the left, it must be E2 to cancel out on the right, essentially.
I see. Um, Prove that for each element A in G1, the f of the inverse is equal to the inverse of f applying A. If G1 is a cycle group with a generator A, prove that. Yeah, I think what Marinho said essentially summarizes it, right? So these things must be true, otherwise the group structure would be violated. Which is okay, easier said than done, right? So, and I'm not saying this is a proof. I'm just saying that again.
Yeah, yeah. No, the devil is in the details, right? You have to actually carry out the proof, but the starting point is if any of those things are false, it's going to violate that condition of respecting the group structure.
Yeah. Yeah, man, this is so cheap of Teseus thing. Again, I think I had the same conclusion when we read the other book, and now the same thing. But now I actually at least I have more ways to describe it, right? We have more vocabulary to talk about it. Okay, so any comment about exercises on B, under B? Okay.
No more comments from me.
Okay, so C. In each of the following, G and H are finite groups. Determine whether or not G. is isomorphic to H. You have to prove your stuff. To find an isomorphism between them, you require a little ingenuity, which is the thing that pisses the shit out of me. Again, this is another time where you have to be quote unquote creative. For example, if G and H are cyclic groups, it is clear that we must match the generator A of G with the generator B of H. Which, by the way, we also read that notion of generators in the category theory book. I remember. We didn't mention that when we read this the first time, but we did read that. Um, that is, if A is equal to B, then the generators will also be mapped and so on. If G and H are not cyclic, we have other ways. For example, if G has an element which is its own inverse, it must be matched with the element of H having the same property. Often, the specifics of our problem will suggest an isomorphism if we keep our eyes open. To prove that a specific one corresponds, we may check that it transforms the table of G into the table of H. And now comes the creative part. G is the checkboard game group in this chapter, exercise D. H is a group of complex numbers, blah blah blah. So my understanding of all these 6 exercises is just this is just a matter, and probably easier if you can just write the tables. And then
Yeah, if you just write the tables, you can figure this out. Oddly enough, most of the pairs that they give are not actually isomorphic to each other. But if you look at some elements of different exercises here, you'll find isomorphisms between them, um, which I found kind of interesting.
yeah. And of course, right? Uh, there's only a subset of cases where you can actually write the table down. Because in the examples of the positive numbers with the other numbers, with addition and multiplication, you cannot write the table for that,
Well,
obviously.
actually, in this particular section, all of those are finite groups, so you can get away with just writing all the tables.
No, no, that is what I was about to say. This should not give you the false impression that you can always do that.
Yeah, no, if you're dealing with a group, like a group based on the rational numbers, for instance, or on the integers, obviously it's going to take literally forever to write down that
And
table,
I
right?
wouldn't even say those. If this was Z28, it's gonna take some time, right?
Well, it's doable, but yeah, it's gonna take a while. It's a 28 by 28 table. That's
Exactly.
kind of big.
Yeah, exactly. So it should not give you the false impression that this is something that you can always be doing. But Maninho is right. In this particular case, you actually can do that. Okay, any comments about C? Okay,
I
go.
learned that the group of integers modulo 4 is isomorphic to those four complex number units, uh,
Yeah, that makes sense.
which I, which I found kind of interesting actually.
Yeah, that actually makes sense. Separating groups into isomorphism classes. So each of the following is a set of 4 groups. In each set, determine which groups are isomorphic to each other. Prove your answers and use A3 where convenient. So A3 is about the transitivity or composition, right?
Yeah,
Um, and we have Z4, pairs of Z2s, P2, which denotes the groups of subsets of 2 elements, and V. And V is the 4 complex numbers. So Z4 and V are isomorphic, as Marinho said, right?
yeah.
What about the other ones?
The other ones are isomorphic to each other because
You mean
you can
these
actually,
two, right?
yeah, the pair of, well, it's a pair of booleans, let's say. It's actually a pair of integers modulo 2, which are isomorphic to booleans. But yeah, turns out you can actually interpret both of those as being about the XOR operation on a 2-bit integer.
Mm-hmm. Mm-hmm. What is there? Are there any other combinations of isomorphisms between those 4?
No,
I don't
there
think so.
isn't.
Yeah. Okay, so true. So we have S3, which is the group of permutations all the way through 3, right? And we have Z6, we have this, and we have Z7 star. And Z7 star denotes multiplication modulo 7. The product modulo 7 of A and B is the remainder of AB after division by 7. So what about those? Is this one?
Uh,
Not sure. I don't think it is actually. Because it's gonna be
yeah,
9 things and this is 6 things.
no, both are 6 actually. But they have different structure, I'm pretty sure.
No. This is modulo 3 and modulo 2, right? These two. Well,
Well, yes.
this pair.
Well,
So
yes.
so how many possibilities we have there, right? Oh no,
Well, 6.
no, you're right. We
Be-
do have 6. But you said your intuition is pointing that we don't have this. They don't have the same structure, right?
Yeah, for similar reasons to why Z4 in the pair of Z2, Z2 above also doesn't have the same structure.
Which one is isomorphic to this thing? The Z6 and this Z7 star?
Let's see, multiplication modulus 7. Um, multiplication modulus 7. Uh, 1 times, yeah, 1 is the identity, so that's 0. 6 times 6 is 36, which is 1, which is the identity. It is its own inverse.
No, so you need to find another element in the other one, which is its own inverse.
Yes, you would have to.
Well, anyway, we have to draw that out. Like nothing too crazy as far as we can tell, right? It's just a matter of finding those things. It's the same principle of understanding that Z4 and V are isomorphic anyway. Um, yeah, yeah. And then I didn't do that. Maybe I should have. Why Z4 and these is not, and this second one is isomorphic. I think that maybe I should do that to see why they are not isomorphic. Because there are 4 elements in both of them, right? Do you remember, Marin, why they are not isomorphic? What didn't match between them?
Uh, it's because in the pair case, the Z2 Z2 pair, every
Hmm.
element is its own inverse, which is not the case for Z4 actually.
Every element is its own inverse. These are both modulo 2's, right?
Yeah,
Ah, I see. Yeah, they are. Well, this is because they are Z2's, right? That's how they got that property.
yeah, and because this is addition pairwise, right? So
Hmm.
1 plus 1 modulo 2 is 0,
Yeah,
and 0 plus 0 modulo 2 is 0. So
yeah. Okay, what about 4 though? Because I'm confused. Aren't those two diagrams the same on the left?
they aren't because the inner arrows go in opposite directions.
Ah, okay. I was just looking at the outer arrows. I'm dumb. Okay, the inner arrows are different. I see. Well, you can represent. This is just another way of encoding these things, so this is fine, right? It's the same exercise, but written in a different way.
Yeah, honestly, I really didn't bother doing the fourth one because the diagrams are nice, but they are really not ideal for this particular exercise. So yeah, I would have to encode it in the other way to figure out the
Yeah.
tables, and
Oh,
it's just
actually,
extra.
maybe the exercise is trying to put the seed in our heads that there is a trivial way of finding isomorphism if it's written this way. Maybe.
Well, I'm pretty sure the first two are not isomorphic because, well, because of the arrows going in opposite directions on the inside.
Yeah. Well, because that's exactly the thing. This is the structure, right? So if the argument is that the structure should be the same, just by looking at it, you should be able to tell.
Yeah.
So that's cool. Okay, so E. We have to speed this up a little bit. So E of infinite groups. So it's the same exercise, but the only one that I think we should try to prove actually is 6. or 5. Because trying to prove that they are not isomorphic, I think would be cool. Because we have seen that this was the case that up there, but he wants to prove to us, well, he wants us to prove that rationals is not isomorphic to the positive rationals under multiplication. And I'm assuming these rationals is under addition.
Yeah, normally it's under addition if you don't have the star.
Yeah, so why are they not isomorphic? That's the question.
Why are they
I
not
have a
isomorphic?
feeling because there may be, okay, maybe this is bullshit. I'm gonna say the disclaimer right away. But I have a feeling that rationals positive on the multiplication is gonna converge a bunch of these numbers because when you multiply different fractions, they go to the same outcome.
Hmm. Oh,
Like
this
I,
is just this is just concerning itself with the positive side. So you don't have the issue of okay, multiplying two negative fractions gives you a positive result, and that obviously collides with the multiplication of the corresponding positive ones, right?
yeah.
That doesn't have this issue because it's just the positive ones to begin with, but let me think for a second. Okay, so you would have to map every negative. Hmm. Yeah, you would have to map every negative rational from the first one to oh, up quite clearly, like 0 goes to 1, right?
Yes,
But
yes.
then,
0 definitely goes to 1. Because 0 is the neutral element of the addition and 1 is going to be the neutral element of the multiplication.
hmm.
Yeah, but again, I have a feeling. No, but this is also true with addition, right? You can always also make the same outcome by doing many different additions, as you could with the same outcome doing very different multiplications.
Hmm.
Yeah, so this is the one that I actually like. These two are more like the problem. Because my intuition of the other ones is kind of like fine, but David, do you have any idea on how to do that one?
Uh,
Not currently. In the other one, we proved that the reals are isomorphic to the multiplicative re- group of the reals of the positive reals by mapping it to
Well, we essentially use
exponentiation.
yeah,
But
exponentiation did all the
we can't
leverage
do
there.
that because
right, because going backwards would be taking a logarithm, right?
Mm-hmm. Yeah, we need to remember that whatever operation we choose, it must be bijective, right? Which means that there must be an inverse. But that's the problem because we cannot prove it's not isomorphic by having a candidate because maybe that's just the wrong candidate, right? We have to prove they are not isomorphic by doing this hint, right? So we have to identify a property which is not particularly about the name of it that one has that the other doesn't have. And I'm not finding that. That's the problem. I'm not finding it. Well,
Hmm.
I'm gonna have to sleep with that one. We can put that on hold for now. So F. This is one is essentially about the generators thing, right? So we have the defining equations that we've seen before in chapter 5.
Yeah.
And you have to check if the following pairs of groups are isomorphic or not. and then you have a transposition here in this permutation, well, this cycle, and you have G prime having those things, and you have also these equalities. This seems all just boring, right? Like just suffering, like a bunch of paper going to the trash.
Yeah, you basically have to figure out the equations for the ones that are not defined in terms of equations and see if it matches with the ones on the right
Mhm,
that are.
mhm, mhm. Okay, I'm gonna assume that we don't have anything else to talk about F. G, isomorphic groups on the set real. G is this set, and then it has this operation. Show that fx being x minus 1 is an isomorphism of without the 0 to G, and thus it is isomorphic to G. Um, I guess you can just like map the 0 to the minus 1 being excluded and seeing if this holds.
Actually, it would be 1, yeah, 0 to minus 1, and then 0 to minus 1.
Yeah,
Yeah, because f of 0 would be minus 1 in this
yeah,
case.
exactly. So it seems fairly natural to do that. G is the set with this operation. Find the and this is actually the hard part. Find the isomorphism between to make it isomorphic. Uh, Assuming this operation on the group, right? So this is where you need to be creative and things like that. I'm not gonna even try to do those ones because man, I'm terrible at those, right? I already told you guys. Every single exercise or thing that requires creativity, that's my burden. That's my problem. And then again, this one is also about finding an isomorphism, and then show is isomorphic to this. Well, you need to prove that there is an isomorphism between that this is an isomorphism between this guy and this guy. To go my elements of that, one multiplies first components, adds second components, because this has addition and this has multiplication, and then you conclude that those are the case. Very weird choice, isn't it? F of x and y is the one, like minus one to the y times x. Very cursed. But you can probably just do the checklist on this one, right?
Yeah,
You have to show that
probably.
this is a bijective, and then that the compositions are kept when you do the
This
loop.
is actually no, intuitively, this is just abstracting the sign because you have the multiplicative group, which is R star, and then you have the positive multiplicative, which is R pos, and then you have essentially a boolean, right? That's the sign, which gives you
Yes,
negatives.
yes, but what's the?
Because R star includes negatives, R pos doesn't, but it's paired with a boolean, so we'll effectively have negatives from the boolean.
Yeah, but what about the zero though? Because our star doesn't have the zero.
There's no zero in either of them.
Oh, but wait. I thought we had zero because of our pos.
No, because they use a definition of positive that does not include zero. So, and R star also doesn't have zero. So,
Oh yeah,
zero
no.
is
If
a
no,
non-issue.
but no, but if that's the case, this is just a more cumbersome way of having integers. Well, not integers, I guess, but the negatives,
Of
as you said,
having
right?
negatives, yeah.
Yeah. Some general properties of isomorphism. So, well, prove. Actually, this is actually a stronger proof, right? You have to prove that the pairs can, if you commute, they are they are isomorphic to the inverse, to the
Yeah,
opposite.
we've seen a bunch of these when we read about category theory.
Yeah. If G1 is isomorphic to G2 and that, yeah, again, you can probably just like, I don't know. Intuitively, this all makes sense, right? But again, this is not as devilish in the details as Marinho said. You're probably gonna have to prove that, assuming, I don't know, you create an F and then you say that you can make another G that make like just swaps the pairs, whatever. Let G be any group. Oh, and then we have the abelian stuff, right? So prove that G is abelian if and only if the function f is equal to its inverse is an isomorphism from G to G. So f is equal to the inverse. That means that it is abelian, which means that now we have commutativity. So how would you guys go about that?
Mm,
I have no idea. Like, I don't see the relationship between being abelian and f just being the inverse.
well, it's because for that to work out, G has to contain the structure of its own inverse inside of itself, right? Maybe that has some implications about whether commutativity exists in the group.
Again, even though I understood what you said, to me, I don't have an intuition between the inverse and being abelian. But I think this is a skill issue because I think we talked about this before in the chapter where we introduced abelian groups. I think this was already discussed that there isn't a relationship between inverse and abelian. Anyway, so then we have 4. Let G be any group with its operation denoted multiplicatively. Let H be a group with the same set as G, and let its operation be defined like that. So again, well, the operation swaps them out. And then we have to prove that G is isomorphic to H. This seems the same exercise as 1, in a way.
Kinda, but not really.
Because this is also doing a swap. But it's
Yes,
a
but
swap
this
in
is
a different level.
yeah, it's a different level. It's a different level.
Let C be a fixed element of G. Let H be a group with the same set as G with the operation that. Prove that the function this is an isomorphism from G to H. Again, every single one that you have to prove that it provides the F, you just have to go through the checklist. So, I, group automorphisms. If G is a group, an automorphism of G is an isomorphism from G to G. Crazy. We have seen that the identity function is an automorphism of G. However, many groups have other automorphisms. So, for example, these F for Z6, which it is bijective and the composition is capped. So it is. And then we also have these Fs for Z5. And like this is very like intuitively clear that they are. But again, you should do the checklist. If G is any group and A is any element of G, prove that blah blah blah. What the heck is this comma doing up there? That's funny.
Yeah,
Is an
that wouldn't be there.
automorphism of G. We've seen this before.
We did last chapter even.
What's the name of that again?
Uh,
There is a name for
there,
that.
there is a name for that.
There is a name. So let's go there. Just for to have the name. Um, but I very clearly remember talking about that the last time. So what is the name? It was not in the chapter itself. I think it was in the exercises of the last time.
Isn't it a conjugate
Conjugates,
from?
conjugate, yeah, it's a
Conjugate.
conjugate.
Yeah, and then Marinho did the demonstration of his IQ by doing it live. I remember. I remember. Which again, it still feels unreal that he just made that on the spot. But okay that he admitted himself that that was an easy case. Okay, so since each automorphism of G is a bijective function from G to G, it is a permutation of G. Yes, of course. Prove the set out of G of all the automorphisms of G is a subgroup of SG. you essentially gonna do the same steps that of the proof that every group
Yeah,
is
that the inverses are there, that you have the identity that is closed over, composition, and so
composition,
on.
inverses, like again the same thing. And then finally J, regular representational groups, which means that you can. It's what I said, right, about the left and the right. You can do the same thing. But if G is abelian, then you there is a new name to remember, which is regular representation. Because then the left and the right are can be done the same because you can just flip them around. I don't know why they
Uh,
introduced this though. Like, seems unnecessary naming. But I guess it's because if the problem states that there is a regular representation, you can already imply that it is abelian, maybe. Maybe that's why. Um, and then we have the regular representation of Z3 consists of the following permutations. So, and this is also very funny because this is exploiting the wraparound, right? So you
uh,
have identity, and then you have add one, which essentially like adds one. So add one, add one, add one, and then true goes to zero because it wraps around, and then pi true is essentially add true, which in this case is just go to the end, and then this becomes a table, and then the function becomes that. It's easily to see seen to be an isomorphism from Z3 to its regular representation, and find the right and left regular representation. Wait, left and right.
yeah, because if it's not abelian, then there's a difference between multiplying on the left and multiplying on the right.
No, yeah, of course, but this name seems a misnomer to me because if you have regular, this implies that they are the same.
No,
But the fact that they are
not
not the same.
no no no. There's a left regular representation and there's a
Ah, it
right
is
regular
here. No, my
representation.
bad, my bad, my bad.
But if the group is abelian, then they are both the same.
No,
Yeah.
no, I forgot that we have regular in the three names. So left, right, and none. All of them are regular. Okay. Then it makes more sense to introduce the name. If the group is abelian, first find its regular representation. So P2, the group of the subsets of two-element set. Z4. Okay, Z4 is essentially going to be this example of Z3, but Z4. And the group G of matrices described on page 8. Okay, so let's try to finish for today. We have 3 minutes. P2. So what would be the representation of those guys?
Uh,
Do
well,
okay, go.
uh, hmm. Well, we would have to basically define the two. You have to define the two. Actually, just one because P2 is it happens to be abelian. So you have to define pi, which is the the
Permutations.
function. Yeah, the function that permutes the group. There are four elements, so if you label them from 0 to 3, um,
Okay,
you
actually I'm
basically
gonna write that because it's only 4 elements. So let's write that.
actually I have the table for that because I actually wrote it earlier when I was reading the book.
So
Um,
Z 0 1 1 1 and I guess 1 0. And then all of that like that. And then you need to do something like that. Oh, if you have the table, you already have all those things, right? So how do you
yeah, I
define
wrote.
pi in this case, though?
Well, we would have pi 0, which is the identity permutation, right? So it goes from 0 to 0, 1 to 1, 2 to 2, and 3 to 3. Of course, you have the binary representation there, but it's doesn't matter too much.
Mm-hmm.
Um, then you have to define pi 1 and pi 2 and pi 3, which are basically um,
Which operation is pi 2? I forgot. Is it multiplication
uh,
or addition?
well, in this case, it's more convenient to represent it as addition because this is in fact commutative, right? It's XOR essentially.
Mm. Okay, and then you're gonna write this table then.
Yeah, and then you have to write the definitions of the pies like that.
Yeah, but in that case, being XOR, you're just gonna like, how should I say? Pi 0 is gonna be
XOR
identity.
with, yeah, it's identity because it's XOR with 0.
Okay, and then you're gonna do XOR with 1,
Yeah,
XOR with true, and
and
so on and
XOR
so
with 3,
forth. So then you're gonna
and
create this table.
then you make the table, then you make the function mapping each element to its corresponding pi, and that's the isomorphism.
What is the rationale between the like? How do you know from which element which pi you're gonna pick? Do you use
The
the table?
subscript, the subscript is the same as the element.
Wait, isn't this the case because of if we are using modulo? Is this always the case?
Well, it's always the case, regardless of the group, right? You have the base group, and then you are defining the pi, which is basically a function that takes an element from the group and
Ah, I guess that
applies
makes
the group
sense.
operation with the elements
Yeah,
that you
with
use to
the element
construct the pi.
itself. Yeah, it's add true. That's why it's pi true. Makes sense. Okay, so next time we're gonna do chapter 10. So order of group elements. I haven't read that, so I don't know what to wait for that. Any comments to finish it off today?
Um, One remark about the question that we were thinking about the abelian groups in isomorphisms, right?
Mm-hmm.
Where was it?
It's
Um,
on. Uh, oh man.
it's age,
Here,
right?
it's H3.
Uh, One tidbit that I think may help is we know that in any group whatsoever, the group operation applied to an element and its inverse is commutative in that special case.
Wait,
So
repeat
maybe
that.
this, like, A times A inverse is equal to A inverse times A, right? In any group, no matter if it's abelian or not, right?
Yes,
Maybe that relates to this. And that's something I thought about.
maybe, maybe. Yeah, but so far I would say that yeah, this chapter isomorphism was fine. I think it was fine. This trick of using the creating the pi, right? Of like multiplying on the left or the right or whatever, this is a cool trick. Cool trick. Any final comments so far before I finish the recording?
I like isomorphisms.
And don't forget it needs to be bijective. I'm gonna finish the recording.